Welcome to this presentation on hydrogen safety and related risks. I'll give a brief introduction, discuss the importance of understanding the safety of hydrogen for future fuel use, and examine its properties in gaseous, liquid and solid forms. I will also highlight potential hazards associated with hydrogen incidents and conclude with key factors for safe operation of hydrogen facilities, whether at the research facility or a filling station. The summary will provide a rounded view of hydrogen hazards and ways to mitigate them for a safe and sustainable future. To manage risks and prevent accidents, it's important to understand the properties of hydrogen. At room temperature, hydrogen is a colorless, odorless, tasteless, non-toxic and non-corrosive gas. It has the lowest density of all gases and the highest speed of sound, allowing pressure waves to travel rapidly. Hydrogen's flammability is a known hazard, and although it's not harmful to breathe, it can displace oxygen and cause asphyxiation. When cooled below -253 degrees Celsius, hydrogen becomes a clear colorless liquid that can pose cryogenic risk due to its low temperature. Physically, liquid hydrogen contains two spin isomers, orthohydrogen and parahydrogen. Although they are chemically identical, conversion to orthohydrogen occurs spontaneously, releasing slightly more energy than is required to evaporate the liquid hydrogen. This effect leads to boiling, even under ideal insulation conditions. The release of this gaseous hydrogen then harbors its own risks. The most commonly discussed hazard associated with hydrogen is the risk of combustion. As with other combustible fuels, an oxidant, such as oxygen from air, is required to form flammable mixtures. The application of ignition energy sets off a chain reaction. This chain reaction can take the form of a fire if it is sustained, a deflagration if its reaction front propagates at subsonic speed, a detonation if the reaction front propagates at supersonic speed. Depending on the situation, there may also be an increase in velocity due to the flame acceleration and thus an increase in pressure. The fire tetrahedron indicates the need for oxidant, hydrogen and heat to enable the hazardous situation of combustion. Removal of any one of these factors will effectively prevent the dangerous chain reaction. Compared to most other fuels such as methane, propane and octane, hydrogen has a wide flammability window at standard temperature and pressures. The graph shows the relative flammability of these gases. Although the self-ignition temperature of hydrogen is quite high, 858 Kelvin or 585 degrees Celsius, its minimum ignition energy of 0.017 millijoule can be readily provided by a variety of sources. These include electrical sources such as electrostatics or short circuits, mechanical sources such as friction or hard impacts, and chemical energy sources such as flames and existing or promoted chemical reactions. Hydrogen flames have a very high temperature of approximately 2045 degrees Celsius, thus posing a significant risk to personnel and equipment. As they radiate mainly in the UV spectrum, hydrogen flames are nearly invisible to the naked eye and are also dangerous in the vicinity due to the UV exposure to skin and eyes. In this image, the flame from the rocket engine is barely visible, but the engine is running. In the event of a deflagration or detonation, the rapid propagation and intense pressurization of up to 120 times the initial pressure is dangerous in itself, but also to the shrapnel formation and damage through fragmentation of nearby equipment. The gas jets themselves pose serious risks to organic tissue. In addition to thermal and chemical hazards, pressurization can also occur from physical effects. It takes very little energy to evaporate liquid hydrogen. This in turn drastically increases the volume, putting the system under pressure. The subsequent increase in volume by more than 850 times increases the risk of rupture or displacement of the liquid cryogenic hydrogen. thereby exposing the environment to high concentrations of hydrogen and very low temperatures. One frequently mentioned effect associated with exposure to hydrogen is the embrittlement of metals. Embrittlement of certain metals occurs at the molecular level. The presence of surface defects allows hydrogen molecules to be absorbed onto the material. Rather than diffusing directly into the metal, H2 dissociates, forming two hydrogen atoms. These atoms then migrate into the metallic lattice structure. Once the hydrogen atoms have diffused into the material, they accumulate at the grain boundaries of the metallic microstructure, where they eventually either recombine to form H2, exerting stress from within by forming gas bubbles in the material, or the atoms react chemically to form hydride species. The microscopic cracks and newly formed hydrides weaken the overall structure integrity, creating a risk of cracking or fracture. Austenitic stainless steels, aluminum and aluminum alloys, and copper are not susceptible to hydrogen embrittlement due to their microstructural composition. This highlights the importance of material selection for hydrogen-containing equipment and machinery. Low temperature hazards are commonly associated with liquid hydrogen, but the release of large quantities of pressurized gas can also significantly cool the surrounding via the Joule-Thomson effect, similar to the cooling of a spray can. At low temperatures, contact with cryogenic burns or frostbite is a threat to organic tissues. Exposure can also cause hypothermia, a drop in body temperature below 35 degrees centigrade, which increases the risk of heart failure. Cryogenic embrittlement is another low-temperature hazard. Since the ductility of metals depends on the number of slip systems within a crystal, and low temperature reduces the mobility of dislocations within the metallic lattice, brittleness increases as temperature decreases. The material is unable to absorb deformation energy and cracks, as can now be seen in this diagram. To mitigate the risk and maintain a high level of safety and awareness, inherent systems such as automatic gas shut-off linked to detectors and warning devices are of paramount importance. The location of the hydrogen system can help prevent gas buildup, limiting the risk of fire, explosion and asphyxiation. Operating in accordance with approved procedures, manuals and instructions will reduce the risk of operator-induced failure of the hydrogen system. Operators must be confident and well trained to prevent leaks, detect them in time with portable detectors or bubble spray, and respond accordingly. Last but not least, the system itself must be maintained in the best possible condition. This includes continuous checking of all valves, filters, and instruments, calibration of warning systems and detectors, and regular replacement of seals, filters, and other components, subject to wear and tear. At the end of this short presentation, we have discussed how hydrogen, although non-toxic, odorless and non-irritating, can pose serious hazards. There are many applications that require either gaseous, liquid or partially solid hydrogen. Each of these forms has different hazard potential, such as pressurization and subsequent sudden gas release, and fragmentation of equipment, high temperature, fire and explosion, low temperature and associated increased risk of fire from air condensation, embrittlement either from hydrogen diffusion or low temperature, and asphyxiation from air displacement. Being aware of the risk does not make it more dangerous. It provides the opportunity for detailed safety measures and risk mitigation strategies. Finally, safe and efficient operation builds confidence in hydrogen technologies and lays the foundation for hydrogen as an energy, economic, and environmentally sustainable fuel of the future.